Hi students, welcome to the 11th lecture in permutations and combinations. I hope you have watched all the previous 10 lectures. In this lecture, we are going to discuss certain theorems related to grouping and few example problems. Before going into the details of this lecture, let me recall what we have done in the previous 10 lectures. So, we have discussed about fundamental principle of counting both multiplication and addition. If a task contains two works W1 and W2, then the number of ways of doing the task is equal to number of ways of completing W1 times number of ways of completing W2. And coming to addition, if a task can be performed in two formats, W1 or W2, then the number of ways of completing the task is equal to number of ways of doing W1 plus number of ways of doing W2. So precisely what you have to remember here is whenever n comes you have to multiply, and whenever r comes you have to add. And then we have defined factorials. We have defined linear and circular permutations. So if you arrange things in a line, then it is going to be a linear permutation. If you arrange things on a circle, then it is going to be a circular permutation. And number of permutations of n distinct objects taken r at a time is in general denoted by npr, and npr is equal to n times n minus 1 times n minus 2 times and so on up to n minus r plus 1. So in general we can write this one as n factorial upon n minus r factorial. Therefore npr is equal to n factorial upon n minus r factorial. That is, number of permutations of n distinct objects taken r at a time is going to be n factorial upon n minus r factorial. And then we have discussed few theorems related to npr. And the first theorem is npr is equal to n times n minus 1 p r minus 1. And the second theorem is npr is equal to n minus 1 pr plus r times n minus 1 pr minus 1. So here r times n minus 1 pr minus 1 stands for number of permutations of n distinct objects taken r at a time, in which always contain a particular object. And n minus 1 pr r stands for number of permutations of n distinct objects taken r at a time which do not contain a particular element. And npr stands for number of permutations of n distinct objects taken r at a time. Therefore, number of permutations of n distinct objects taken r at a time is equal to number of permutations of n distinct objects without containing a particular object plus number of permutations of n distinct objects which always contains a particular object. Next, if repetitions are allowed, then the number of permutations of n distinct objects taken r at a time is going to be n raised to r. If repetitions are not allowed, then it is going to be npr. Now, number of permutations of n distinct objects in which at least one object is repeated is going to be n raised to r minus npr. N raised to r gives the number of permutations when repetitions are allowed, and npr stands for number of permutations of n distinct objects taken r at a time when repetitions are not allowed. Therefore, n raised to r minus npr gives the number of permutations in which at least one object is repeated or one element is repeated. And then we have defined palindromes. If a word or a number reads the same from left to right or right to left, then it is called as a palindrome. Now, number of palindromes of length r obtained by, number of palindromes of length r formed using n objects is going to be n raised to r upon 2 or n raised to r plus 1 upon 2. So we have to use n raised to r upon 2 when r is an even number, and n raised to r plus 1 upon 2 when r is an odd number. Depending upon the length of the palindrome, we have to use these formulas. And then we have defined circular permutations. And the number of circular permutations of n distinct objects taken all at a time is going to be n minus 1 factorial. So in these circular permutations, there is a special exception. So that is hanging modals. So in case of hanging modals like garland of flowers or chain of beads, clockwise and anti-clockwise permutations are treated as a single permutation. Therefore, number of permutations is going to be n minus 1 factorial upon 2. So why we have to divide it by 2 means we are treating clockwise and anti-clockwise permutations as a single permutation. So if I want to interchange these two people, these two extreme people, then what I have to do is I have to make them stand and I have to interchange their places. So that is the only way to change these two positions. And whereas if I want to change these two beads, if I want to change the positions of these two beads, then what I can do is I can just rotate this chain. So if you view this chain from the front, then this is to your right side and this is to your left side. If you view this chain from back side, then this one will be to your right side and this one will be to your left side. That means both clockwise and anti-clockwise permutations are treated as a single permutation. Next, we have permutations with constraints. In a set of n objects, if p objects are alike and the remaining are distinct, then the number of permutations of these n objects is going to be n factorial upon p factorial. So if p objects are alike, then the formula is going to be n factorial upon p factorial. Formula in the sense number of permutations is going to be n factorial upon p factorial. If in a set of n objects, p objects are alike, q objects are alike and r objects are alike, then the number of permutations of these n objects is going to be n factorial upon p factorial times q factorial times r factorial. And then we have defined what is a combination. So in case of combinations, order does not matter. Number of combinations of n distinct objects taken r at a time is going to be npr upon r factorial. That is, n choose r is equal to npr upon r factorial, which is going to be n factorial upon n minus r factorial times r factorial. I repeat, number of combinations of n objects taken r at a time is going to be npr upon r factorial. In general, we denote the number of combinations of n objects taken r at a time by ncr, and we read it as n choose r. So n choose r is equal to npr upon r factorial, which is equal to n factorial upon n minus r factorial times r factorial. We have given the proof of this one in the last lecture. In general, ncr or n choose r is equal to npr upon r factorial, which is going to be, and npr is equal to n times n minus 1 times n minus 2, so on up to n minus r plus 1. And r factorial means r times r minus 1 times r minus 2 and so on up to 2 times 1. So in the numerator we have r distinct r conjugative terms, and in the denominator we have r conjugative terms. And in the numerator it starts with n. In the denominator it starts with r. Now, number of subsets with r elements of a set containing n elements is going to be n choose r. I repeat, number of subsets with r elements of a set containing n elements is going to be n choose r. So whenever you see this n choose r, you can treat it as number of subsets with r elements of a set containing n elements. Next, we have proved this theorem in the last class. N choose r is equal to n choose n minus r. So I repeat, n choose r is equal to n choose n minus r. So selecting r objects from n objects is same as removing n minus r objects from n objects. For example, if there is a class containing n elements or n students, I have to select r students, and the number of ways of selecting r students is going to be n choose r. So instead of selecting r students, what I do is I remove n minus r students. Number of ways of removing n minus r students is n choose n minus r. After removing n minus r students, we will have r students. Therefore, n choose r is same as n choose n minus r. Now we have a corollary of this theorem. That is, n choose n is equal to n choose 0 is equal to 1. N choose n is equal to n factorial upon n minus n factorial times n factorial. So which is equal to n factorial upon 0 factorial times n factorial, which is equal to 1. But we know that n choose r is equal to n choose n minus r. So let r is equal to n. So this implies n choose n is equal to n choose n minus n, which is nothing but n choose 0. Therefore n choose n is same as n choose 0, which is same as 1. Next we have a small example problem. If a set A has 8 elements, find the number of different subsets of A containing at least 6 elements. So there is a set A which contains 8 elements. Now I have to find all the subsets of A which contains at least 6 elements. So cardinality of A is equal to 8. That means the set A contains 8 elements. Now number of subsets with at least 6 elements is equal to number of subsets with exactly 6 or exactly 7 or exactly 8. I cannot go beyond 8 because the cardinality of A is 8. That means the number of subsets, number of elements in A is going to be 8. I cannot have a subset containing 9 elements. Okay, so at least 6 means it can be either 6 or 7 or 8. Now number of subsets of A containing 6 elements is going to be 8 choose 6. Number of subsets of A containing 7 elements is going to be 8 choose 7. Number of subsets of A containing 8 elements is going to be 8 choose 8. So the total is going to be 8 choose 6 plus 8 choose 7 plus 8 choose 8. 8 choose 6 stands for selecting a subset containing 6 elements. 8 choose 7 stands for selecting a subset containing exactly 7 elements. 8 choose 8 stands for selecting a subset with exactly 8 elements. So at least 6 means it can be either 6 or 7 or 8. Or simply it starts with 6 and more. Okay. Next, this is our main theorem in the lecture. If m comma n are positive integers, then the number of ways of dividing m plus n distinct objects into two groups containing m things and n things is going to be m plus n factorial upon m factorial times n factorial. So let me explain the statement for you. So m and n are positive integers and there are m plus 1 distinct objects. Objects are things. And the number of ways of dividing these m plus n things into two groups containing m elements and n elements is going to be m plus n factorial upon m factorial times n factorial. So first let us try to understand what we have to do. We have to divide m plus n different things into two groups, each containing m and n elements respectively. Now selecting m elements means, now if we select m elements, then we are left with m plus n minus m, that is n elements. So if you select m elements, then you will have m elements, and the number of elements that are going to be left out is n elements. So I have two groups. So the first group is the selected m elements, and the second group is the remaining n elements. So if I want to divide m plus n elements into two groups containing m elements and n elements, all I have to do is I have to select m elements. If I select m elements, then automatically I will have m elements, and the leftover elements is going to be n elements. Therefore, number of ways of dividing m plus n elements into two groups containing m elements and n elements is same as selecting m elements out of m plus n elements. So this implies number of ways of dividing into groups is same as number of ways of selecting m elements. Out of m plus n elements. So this can be done in m plus n choose m ways. So which is equal to m plus n factorial upon m plus n minus m factorial times m factorial, which is equal to m plus n factorial upon m factorial times n factorial. Therefore, number of ways of dividing m plus n distinct objects into two groups containing m elements and n elements is going to be m plus n factorial upon m factorial times n factorial. So dividing m plus n objects into two groups containing m elements and n elements is same as selecting m elements out of m plus n elements. So if you select m elements, then you will be having m elements, and the leftover elements are going to be n. That means you have divided m plus n objects into two groups containing m elements and n elements. Therefore, number of ways of dividing is same as number of ways of choosing. So number of ways of choosing m elements out of m plus n is going to be m plus n choose m, and m plus n choose m is equal to m plus n factorial upon m plus n minus m factorial times m factorial, which is going to be m plus n factorial upon m factorial times n factorial. So these are the total number of ways of dividing m plus n distinct objects into two groups containing m objects and n objects. Now we can generalize this result, or let us take this result to one more step. If m comma n comma p are positive integers, then the number of ways of dividing m plus n plus p distinct objects or distinct things into three groups containing m things, n things and p things is going to be m plus n plus p factorial upon m factorial times n factorial times p factorial. So let me give the proof of this one. We have to divide m plus n plus p objects into three groups. M plus n plus p objects into three groups containing m objects, n objects and p objects. So first what we do is we select m objects. So let w1 is equal to selecting m objects from m plus n plus p. So therefore cardinality of w1 is equal to m plus n plus p choose m, and w2 stands for selecting. So after selecting m elements out of m plus n plus p, we will be left with n plus p objects. Now w2 stands for selecting n objects or n things from n plus p things. So this can be done in n plus p choose n ways. So after selecting n objects from n plus p objects, we will be left with p objects. So after performing W1, we'll be left with, we'll be having m elements. After performing W2, we'll be having n elements, and the leftover elements is going to be p. Therefore, number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2. And or else if you are interested, you can write down W3 also. W3 is to select p objects or p things from p things. So this can be done in p choose p ways. Now number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2 times number of ways of doing W3, which is going to be m plus n plus p choose m times n plus p choose n times p choose p. Which is equal to m plus n plus p factorial upon m plus n plus p minus m factorial times m factorial times n plus p factorial upon n plus p minus n factorial times p factorial, and p choose p is going to be 1. So which is equal to m plus n plus p factorial upon n plus p factorial times m factorial and n plus p factorial upon p factorial times or n factorial. So here it is not p factor, n factor. So which is going to be m plus n plus p factorial upon m factorial times n factorial times p factorial. So these two terms gets cancelled. So the number of ways of dividing m plus n plus p distinct objects into 3 groups containing m elements, n elements and p elements is going to be m plus n plus p factorial upon m factorial times n factorial times p factorial. In the previous theorem, we have m plus n distinct objects. Number of ways of dividing m plus n distinct objects into 2 groups containing m objects and or m things and n things is going to be m plus n factorial upon m factorial times n factorial. So here we are dividing m plus n plus p things into 3 groups containing m elements, n elements and p elements. And the number of ways of doing it is going to be m plus n plus p factorial upon m factorial times n factorial times p factorial. Now the number of ways of dividing 6 elements into 2 groups containing 2 elements and 4 elements is 2 plus 4 factorial upon 2 factorial times 4 factorial. So we are using this result m plus n factorial upon m factorial times n factorial. So on the whole we have 6 elements 1, 2, 3, 4, 5, 6. The number of ways of dividing these 6 elements into 2 groups containing 2 elements and 4 elements is going to be 2 plus 4 factorial upon 2 factorial times 4 factorial. So 2 plus factorial upon 2 factorial times 4 factorial is equal to 6 factorial, which is 6 times 5 times 4 times 3 factorial upon 2 factorial times 3 factorial. So 2 factorial times 4 factorial. So which is going to be 6 times 5 upon 2, which is going to be 15. And these are the 15 ways of dividing these 6 elements into 2 groups containing 2 elements and 4 elements. So we have 1, 2, 3, 4, 5, 6. I am dividing these 6 elements into 2 groups containing 2 elements and 4 elements. So the first group contains all 2 element groups. And this column contains all 2 element groups or 2 thing groups. And this column contains all 4 thing groups. So pause the video and have a look at this division. Now, the previous theorems are applicable only if these 3 integers are different, or m plus m and n are different here. And in this case, m, n and p, all these 3 integers should be different. So what happens if m is equal to n here? The number of ways of dividing 2n distinct things into 2 groups containing n elements each is going to be 2n factorial upon n factorial times n factorial. That is our basic intuition. What happens if m is equal to n? If m is equal to n, then what we will have is 2n factorial upon n factorial times n factorial. But that is not going to be true. So we can see it here. The number of ways of dividing 2n distinct objects or 2n distinct things into 2 groups, each containing n things, is going to be 2n factorial upon 2 factorial times n factorial times n factorial. So why we are having this 2 factorial, we will see it using an example, and then we can look into the proof. Okay. Now we have these 6 elements, 1, 2, 3, 4, 5, 6. Then the number of ways of dividing these 6 elements into 2 groups, each containing 3 elements. So if you use the previous formula in the sense, if you use this formula, n plus n factorial upon m factorial times n factorial. So here m is equal to 3 and n is equal to 3. Then what you will have is 6 factorial upon 3 factorial times 3 factorial, which is going to be 6 into 5 into 4 upon 3 factorial, which is going to be 20. So there are 20 ways in which you can divide these 6 objects or 6 things into 2 groups, each containing 3 elements each. And these are my 20 distinct arrangements or distinct groups. These are the 20 ways in which I can divide these 6 objects into 2 groups, each containing 3 elements. So pause the video and have a look at this division. So 1, 2, 3, 4, 5, 6. 1, 2, 4, 3, 5, 6, and so on. And then we can continue. So these are my 20 ways of dividing these 6 objects into 2 groups containing 3 elements each. So if you observe this partition and this partition. So if you observe this partition is 1, 5, 6 and 2, 3, 4. And this partition is 2, 3, 4 and 1, 5, 6. Both are the same. So instead of getting 20 divisions, I will have only 10 divisions. So these 10 divisions are in some way a duplicate copy of these 10 divisions. I repeat, these 10 divisions are in some way a duplicate copy of these 10 divisions. So in general, I am not going to get these 20 divisions. I am going to get only these 10 divisions. Why I am going to get these 10 divisions means because these 2 arrangements are considered as a single arrangement, or these 2 tables are considered as a single table. Therefore, the number of ways of dividing 6 elements into 2 groups containing 3 elements each is going to be 6 factorial upon 3 factorial times 3 factorial divided by 2 factorial. So, which is equal to 6 factorial upon 2 factorial times 3 factorial times 3 factorial. So, in general, we have this result. So we have 2n distinct objects or 2n distinct things, and the number of ways of dividing these 2n distinct things into groups, 2 groups containing n things, each is going to be 2n factorial upon n factorial times n factorial times divided by 2 factorial, or 2n factorial upon 2 factorial times n factorial times n factorial. So these are the total number of ways of dividing 2n distinct objects into 2 groups containing n elements each. So here we have this extra luggage of 2 factorial. If m and n are distinct integers, then the answer is going to be m plus n factorial upon m factorial times n factorial. But when m is equal to n, we'll have this extra term 2 factorial. Why we'll have this extra term means these two arrangements are considered as a single arrangement, or these two divisions 156 234 and 234 156. These two divisions are considered as a single division. I cannot say that this is my first group and I cannot say that this is my second group. All that I can say is this is one group and this is one group. There is no first group and there is no second group. In the previous example, I can say that this is first group and this is second group. There is some distinction between these two groups, because this group contains 2 elements and this group contains 4 elements. So I can name this group as 2. I can name this group as 4. But here in this problem, I cannot name these groups differently. So the name of this group is 3 and the name of this group is 3. So we'll have this extra 2 factorial in the denominator. Okay, let us give the proof. Number of ways of dividing 2n distinct objects or distinct things into groups containing n elements each is 2n factorial upon n factorial times n factorial. But here these two groups have the same number of elements. So we cannot distinguish these two. Or these two are identical. Therefore, number of ways of dividing is equal to, therefore number of ways of dividing is equal to 2n factorial upon n factorial times n factorial divided by 2 factorial. So which is going to be 2n factorial upon 2 factorial times n factorial times n factorial. Anyway, proof is not that important. You have to just remember the statement of the theorem. So you can remember the statement of the theorem without any mistakes if you can understand the proof. So if you are good at by hearting the statement, then you can by heart it. Else you have to understand the proof. or else you have to understand this example. If you understand this example, then you will understand why we are having this extra term 2 factorial in the denominator. Okay, let us try to generalize this result. This result in the sense, let us try to generalize this result. And the generalization is like this. The number of ways of dividing mn distinct things into m groups, each containing n elements, is going to be mn factorial upon m factorial times n factorial raised to m. I repeat, the number of ways of dividing mn distinct things into m groups, each containing n elements, is going to be mn factorial upon m factorial times n factorial raised to m. So if m is equal to 2, if m is equal to 2, then what happens? Then we'll have 2n factorial upon 2 factorial times n factorial raised to 2, which is nothing but n factorial times n factorial. That is our previous result. So if n is greater than 2, then we'll have this result. This is the more generalized result. The number of ways of dividing mn distinct things into m groups, each containing n elements, is going to be mn factorial upon m factorial times n factorial raised to m. So in general what we have is mn factorial upon m factorial times n factorial times so on up to n factorial. We'll have m terms. So we'll have n factorial raised to m. But all these groups are identical. Therefore we have to divide it by m factorial. Since all these m groups are similar, we have to divide it by m factorial. So here in this previous case, so I can treat this as the first element and this as the first group and this as the second group. I cannot interchange these two groups because this group is different from this group. In the sense, the number of elements in this group is different from the number of elements in this group. So these are two distinct groups. But here these are two identical groups. The name of this group is 3 and the name of this group is 3. Since these two are similar groups, we have to divide it by 2 factorial. That's why we have this result. 2n factorial upon n factorial times n factorial divided by 2 factorial, or 2n factorial upon 2 factorial times n factorial times n factorial. So the more generalized result is like this. Mn factorial upon m factorial times n factorial raised to m. These are the total number of ways of dividing mn distinct objects into m groups, each containing n elements each, is mn factorial upon m factorial times n factorial raised to m. Next we have an interesting corollary. The number of ways of distributing mn distinct things among m people equally is going to be mn factorial upon n factorial raised to m. Let me explain the corollary for you. There are mn distinct objects or distinct things. I have to distribute these mn distinct things among m people equally. And the number of such divisions or number of such distributions is going to be mn factorial upon n factorial raised to m. So let me give the proof for this. So I have to distribute mn objects among m people. I have to distribute mn distinct objects, distinct things among m people. So first what I do is I divide this task into two groups, W1 and W2. So here W1 is to divide mn things into m groups. W2 is to distribute those groups. This implies number of ways of doing W1 is equal to mn factorial upon m factorial times n factorial raised to m, and number of ways of doing W2 is equal to m factorial. Therefore, number of ways of completing the task is equal to mn factorial upon m factorial times n factorial raised to m times m factorial. So this m factorial gets cancelled, so finally we'll have this results. Mn factorial upon n factorial raised to m. So you can understand this result using this one. So I have 2n distinct objects. Now I have to divide these 2n distinct objects. I have to distribute these 2n distinct objects among 2 people. The number of ways of distributing these 2n distinct objects among 2 people is going to be, first what I have to do is, first I have to divide these 2n distinct objects into 2 groups. Then the number of ways of dividing these 2n distinct objects into 2 groups is going to be 2n factorial upon 2 factorial times n factorial times n factorial. Now these are the total number of ways of dividing the things. After dividing the things, we have to distribute. I can distribute among 2 people in 2 factorial ways. Therefore, the total number of distributions is going to be 2n factorial upon 2 factorial times n factorial times n factorial times 2 factorial. So, which is going to be this one. So if you want to distribute among m people, the first thing that you have to do is you have to divide the groups. You have to divide the things. After dividing, then you can distribute. So dividing can be done in these ways, and distribution can be done in these ways. Therefore, the total task can be completed in these ways. That is nothing but mn factorial upon n factorial raised to m. Let us solve few example problems, and the first problem is like this. A candidate is required to answer 6 out of 10 questions, which are divided into 2 groups A and B, each containing 5 questions, and he is not supposed to answer more than 4 questions in each group or from each group. In how many ways he can select these 6 questions? So try to understand the question. So a candidate is required to answer 6 questions out of 10 questions. So these 10 questions are not in order. In order in the sense, these 10 questions are divided into 2 groups, A and B. Each group contains 5 questions. So group A contains 5 questions and group B contains 5 questions. Group A contains 5 questions and group B contains 5 questions. Now he is supposed to answer 6 questions, but he is not supposed to answer more than 4 questions from each group. So what he can do is, he can select 4 questions from group A and the remaining 2 from group B, or he can select 3 questions from group A and 3 questions from group B, or he can select 2 questions from group A and 4 questions from group B. He cannot select 1 question from group A and 5 questions from group B, because he is not supposed to answer more than 4 questions from any group. So the number of ways of choosing 6 questions is, he can select 4 questions from group A and 2 questions from group B, or he can select 3 questions from group A and 3 questions from group B, or he can select 2 questions from group A and 4 questions from group B. Now this can be done in, so he can select 4 questions from group A and 2 questions from group B. This can be done in 5 choose 2, if I choose 4 times, if I choose 2 ways. He can select 4 questions out of 5 questions from group A in 5 choose 4 ways, and he can select 2 questions out of 5 questions from group B in 5 choose 2 ways. Therefore, he can select 6 questions from the question paper in 5 choose 4 times 5 choose 2 ways. Next, he can select 3 questions from group A and 3 questions from group B in 5 choose 3 times 5 choose 3 ways. And he can select 2 questions from group A and 4 questions from group B in 5 choose 2 times 5 choose 4 ways. Therefore, the total number of ways of selecting is equal to, you have to add these 3. So this is going to be your answer. So here you have to be a little bit careful. The number of ways of answering 6 questions is, he can select 4 from group A and 2 from group B, or 3 from group A and 3 from group B, and 2 from group A and 4 from group B. So these are the only ways in which he can select. And number of ways of doing this one is here, number of ways of doing this job is here, and the number of ways of doing this one is here. So the number of ways of completing the task is equal to number of ways of doing in this format plus number of ways of doing the job in this format plus number of ways of doing the job in this format. So this is your total answer. Now let us move on to the second question, or first solved problem. The next question is like this. Find the number of ways of selecting 4 boys and 3 girls from a group containing 8 boys and 5 girls. So we have to select 4 boys and 3 girls from a group containing 8 boys and 5 girls. So W1 is to select 4 boys from 8, and this can be done in 8 choose 4 ways. And W2 is to select 3 girls from 5, and this can be done in 5 choose 3 ways. Therefore, number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is going to be 8 choose 4 times 5 choose 3. No need to expand these things. You can leave the answer as it is. The next problem is like this. Find the number of ways of selecting 4 English, 3 Telugu and 2 Hindi books from a set of 7 English, 6 Telugu and 5 Hindi books. So this problem is similar to the previous one, so I leave this problem for you. So let us move on to the next one. Now find the number of ways of forming a committee with 4 people from 6 boys and 4 girls, so that the committee contains at least 1 girl. So we have to form a committee with 4 people. So from 6 boys and 4 girls. We have 6 boys and 4 girls. And I have to form a committee with 4 people. So in that we should have at least 1 girl. At least 1 girl means I can have 1 girl and 3 boys, or I can have 2 girls and 2 boys, or I can have 3 girls and 1 boy, or I can have 4 girls and 0 boys. So we have to count in how many ways I can select 3 boys from 6 and 1 girl from 4, plus in how many ways I can select 2 from 6 boys and 2 from 4 girls, plus the number of ways of selecting one boy from 6 boys and three girls from 4 girls, plus number of ways of selecting 0 boys from 6 boys and and 4 girls from 4 girls. So you can do it in this way. You can write the answers here. So this can be done in 6 choose 3 times 4 choose 1, and this can be done in 6 choose 2 times 4 choose 2, and this can be done in 6 choose 1 times 4 choose 3, and this can be done in 6 choose 0 times 4 choose 4. You can add all these things. So you can do it in this way, or else what you can do is total number of ways of forming the committee. Forming the committee is 10 choose 4. So we have 10 people, we have to select 4. Now number of committees in which there are no girls is equal to 6 choose 4. I can select all the boys, but selecting all the boys is not the desirable thing. This implies at least one girl is equal to total minus this one. So which is equal to total is 10 choose 4 minus 6 choose 4. So you can do it in this format or you can do it in this format. Both gives the same answer. Next we have this problem. Find the number of ways of selecting 11-member cricket team from 7 batsmen, 6 bowlers and 2 wicket keepers, so that the team always contains 2 wicket keepers and at least 4 bowlers. So first let us write down the information that we have. So we have 7 batsmen and 6 bowlers and 2 wicket keepers. Now we have to form a cricket team consisting of 11 people, so that it always contains exactly 2 wicket keepers and at least 4 bowlers. At least 4 bowlers means it can have 4 bowlers, or it can have 5 bowlers, or it can have 6 bowlers. But the team should contain always 2 wicket keepers. So if the team consists of 2 wicket keepers and exactly 4 bowlers, then how many batsmen I can choose? So total is 11. So 11 minus 6, which is 5. I can choose 5 batsmen, 4 bowlers and 2 wicket keepers. And this can be done in 7 choose 5 times, 6 choose 4 times, 2 choose 2. Or else what I can do is I can select 5 bowlers and 2 wicket keepers. 2 wicket keepers are compulsory. So I can select 2 wicket keepers and 5 bowlers. If I select 2 wicket keepers and 5 bowlers, I can choose 4 more batsmen. And this can be done in 7 choose 4 times, 6 choose 5 times, 2 choose 2. So if the team consists of 6 bowlers, so it already consists of 2 wicket keepers, therefore 2 plus 6 8, so I can choose remaining 3 batsmen. And this can be done in 7 choose 3 times, 6 choose 6 times, 2 choose 2. Now the number of ways of selecting the team is equal to, you have to add all these things. So plus. So here you can understand that whenever R comes, you have to add. So these are the total number of ways in which I can select a cricket team with exactly 2 wicket keepers and at least 4 bowlers. And the next problem goes like this. If a set of m parallel lines are intercepted by another set of n parallel lines, which are not parallel to the first set of m parallel lines, then find the number of ways of selecting a parallelogram from the lattice structure. So you have to find how many parallelograms can be formed here. So we have m parallel lines of one set, 1, 2, 3, so on up to m. So these are my m parallel lines. And we have another set of n parallel lines. These are my n parallel lines. Now these m parallel lines are intercepted by these n parallel lines. Now we have to form a parallelogram, or number of parallelograms. We have to count how many parallelograms are there in this lattice structure. So in order to form a parallelogram, we should have 4 sides. That means we should have at least 2 sets of parallel lines. We should have 2 sets of parallel lines. That means I have to select 2 lines from the first set, and I have to select 2 parallel lines from the second set. So in order to form a parallelogram, we have to select 2 lines from each set. This can be done in m choose 2 times n choose 2 ways. So I can select 2 lines from the first set of m lines, and I can select another 2 lines from the second set of n lines. So I can select 2 lines from these m lines in m choose 2 ways, and I can select 2 lines from these 2 in n choose 2 ways. Therefore the total number of ways of selecting a parallelogram is m choose 2 times n choose 2.